All right, solutions review. So if we take a look, these are the formulas that we need to make sure that we have. This is the dilution formula, M1V1 equals M2V2, and these are the boiling point and freezing point formula. Don't forget the general molarity formula is moles over liters. The solute is dissolved. The solvent does the dissolving. If something is saturated, it has the max amount of solute for that temperature. And volume solvent. Keep that in mind. Miscible. Miscible means that they can mix. Immiscible means they do not mix. Unsaturated is anything less than the maximum amount. It's going to be anything from one very tiny particulate all the way up to just under saturated. Supersaturated is a very special case where you have more than the maximum amount. A colloid. A colloid is when particles stay suspended in a solvent. So for example, like orange juice or whatnot, you have the pulp all the way throughout it. It stays suspended. Or toothpaste, the grit stays suspended in the toothpaste. Versus a suspension would be like chocolate milk. The particles fall due to gravity. Tyndall effect. Tyndall effect is the reflection of light of particles in a solution. We said yesterday, as the sunlight comes into the windows, you may see dust particles in the air reflecting light. Or if you've ever seen a movie where they have laser beams to protect the safe or something like that, and the villain or the hero takes some type of powder and spreads it out into the room, and then you can see all the laser lights. Electrolyte is an ionic compound. Remember, these dissociate when dissolved in water. Non-electrolyte is non-ionic or covalent compound. We said molarity is moles per liter. Molality is moles per kilogram. That's a lowercase m. Moles per kilogram is molality, and uppercase m is moles per liter of solution. Likes dissolve likes. We talked about how fats dissolve other fats and oils, and water-soluble things or polar things dissolve other polar things. If we increase the temperature, we can dissolve more solids. If we increase the temperature, gases tend to not dissolve as well. Putting pressure on a system does not affect the solubility of solids, but it does affect the solubility of gases. Compare dissolution of ionic versus molecular solids. We say ionic dissociate. Molecular do not. Solubility data graph, we have that below, and then lab information when we found out the molarity of that solution by vaporizing off the water. So let's take a look down here. For the following, identify whether the substance will disappear or dissolve in a polar or non-polar solvent. This is ionic. It starts with a metal. So we know that that will dissolve in polar for sure. Carbon is not a metal. And it's not a polar compound. C is in the middle, and all of these Cl's are going to pull in opposite directions. So this will be non-polar. HCl, if we look at the electronegativity difference here, it is great enough to be polar. So that will dissolve in polar substances. The fact that we have this OH here, that will be polar. That is known as alcohol. And we said alcohols are polar because of this OH. And they also exhume hydrogen bonding. A CS is a difficult one, but if we draw out the Lewis structure for it, we can see that these will cancel each other out. So that is going to be non-polar because the actual polar bonds cancel each other out. Looking below, we have the solubility curves. Which compound solubility is most affected by a temperature change? Well, as we increase, this one looks like it has the greatest slope. So A is going to be affected most by a temperature change. Which of the four, guys, only see three, but which of the three is a gas probably? Anybody? Which of the three would be a gas? As we increase temperature, gas solubility goes what? Yeah, it goes down. So that's going to be C. If you determine that the solubility of each substance is at point X, which of the substances will be unsaturated? So if we are here, we are above C. So C would be supersaturated. Supersaturated in that instance. So who would be unsaturated? Well, we didn't reach up to here for B, and we certainly didn't reach up to here for A. So A and B would both be unsaturated if we only had this many grams at this temperature. Is pure water an electrical conductor? No, it does not conduct electricity well. Why do electrolytes conduct electricity? They dissociate into positive and negative ions, which can transmit electrons. Two colligative properties we discussed: freezing point and boiling point. What did we say happens to the freezing point as we dissolve more stuff? It goes what? Down. It's depressed. And boiling point goes up. It's elevated. If ethanol boils at 78 degrees Celsius, then what kind of boiling point would we expect to see for a solution containing sugar dissolved in ethanol? Higher than 78. Be able to recognize that ionic compounds dissolve in a process called dissociation. So CaCl2 becomes a calcium 2 plus and 2 Cl negative ions. For most solids dissolved in water, the solubility increases as you increase temperature. Three factors that affect how quickly a solid dissolves into a liquid: temperature, agitation, and surface area. For gases in water, the solubility decreases. We talked about how during the summertime, if the temperature gets so high that the actual fish, the oxygen dissolved, will cause the fish to actually suffocate. Suspensions or colloids differ from solutions. Solutions look identical throughout. Solutions look the very same throughout. Suspensions and colloids have particles you can see. For example, if you take a look at like skim milk or something like that, you'll see that you see the actual milk fat inside of there. You'll see the milk fat inside of there. A beam of light is visible when it passes through a transparent suspension or colloid. So that's like we said, if you shoot a laser beam and then have dust in the particle or particles in the air, that's known as the Tyndall effect. That's the concept. Now we just have the math. So remember, molarity is moles per liter. If we have 2.1 moles and 5 liters, we take the moles, we divide it by the liters. 2.1 divided by 5.
It's 0.42.
0.42 has 2 significant digits, but so does 2.1. So does 2.1. Then we can use a big M with a line under it to show molarity. There we go. Next one, calculate the milliliter volume of 0.25 moles per liter solution that would contain precisely 0.0625 moles of dextrose. Now, they've given you the molar mass of these. If they didn't, you would have to add these up from the periodic table. So we want milliliters. That's 1 unit. So this is moles per liter and this is mole. So we want to start with 1 unit. Since I have mole, I want mole on the bottom. Every 0.25 moles is 1 liter by the molarity. That is moles per liter. I don't want liters though, I want milliliters. So every 1 liter is 1,000 milliliters. 0.0625 divided by 0.2 times 1,000.
That would be 312.5.
I only have 3 significant digits. I only have 2 significant digits. So 312.5 will have to be equal to 310 milliliters. You want to prepare 500 milliliters of potassium nitrate solution at a concentration of 0.8 molar by diluting a stock solution. The concentration of the stock solution is 4.00 moles per liter. How many milliliters of stock solution should you use? This is M1V1 equals M2V2. We are trying to solve for V1, the volume of the stock solution. So we need to divide both sides by M1. So we have we want 500 milliliters of 0.8 molar solution. We're going to divide that by 4.00 molar. Molar cancels out. 0.8 times 500 divided by 4.
It's 100.
We need to start with 100 milliliters of the stock solution. We can only have 2 significant digits here, so that's going to change to 1.0 times 10 to the second milliliters if we wanted to show that with the correct significant digit. Questions so far? If you were to evaporate all the water from 0.500 liter of aqueous 1.25 molar NaCl, then how many grams would be left? All the water? We want grams of NaCl. 0.500 liter. Every 1 liter has 1.25 moles. Every 1 mole from the molar mass is 58.5 grams. Point 0.5 times 1.25 times 58.5.
It's 36.5625.
3 significant digits, so it becomes 36.6 grams of NaCl. That's the laboratory you did where you evaporated everything off. You have 0.35 moles per liter potassium chromate solution. How many liters of this solution contain 10 grams of potassium chromate? So we want liters. We want to know how much 10 grams, how many liters would be hold 10 grams of this solution. So every 194.2 grams is 1 mole of potassium chromate. Every 0.35 moles is 1 liter of potassium chromate. 10 divided by 194.2 divided by 0.35.
It's about 0.1471.
3 significant digits, 0.147 liters. What volume in milliliters of 3.00 molar sodium hydroxide is needed to prepare 500 milliliters of a 0.750 molar sodium hydroxide? So we have 2 molarities. So this tells us we are doing M1V1 equals M2V2. We are trying to solve for the volume of V1. So that means we're going to divide both sides by M1. M1 will cancel out here, and we get 0.75 molar times 500 milliliters divided by 3. 0.75 times 500 divided by 3.
It's 125.
And notice molarity cancels out. We're left with milliliters. What is the boiling point of an aqueous solution that contains 31.2 grams of calcium bromide in 375 grams of water? We remember delta T sub B equals I molality times KB. So what we need to do is we need to take and find the molality. 381.2 grams over 375 grams of water. So we change the grams of water to kilograms. And we need to change the grams of calcium bromide to moles. That will give us our molality, moles per kilogram. 40.08 plus 79.90 times 2.
It's 199.88.
We obtain the molar mass from the periodic table to be 199.88. 31.2 divided by 375 times 1,000 divided by 199.88.
It's about 0.4162.
0.416 molal. So that's going to go here. For calcium bromide, what is my index? Is calcium a metal? Find calcium on the periodic table of elements. Is calcium a metal? Anybody? Calcium a metal? Here's calcium on this side of the periodic table of elements. Is this side of the metals? Yeah, Brianna got it. That is a metal. So that means we need to break this down. So the index is going to be 3. So we get 3 times 0.416. And the KB, that's molality. The KB is 0.512 degrees Celsius per molal. Molality is going to cancel out. We're going to end up with degrees Celsius. 3 times 0.416 times 0.512.
The answer is about 0.6389.
3 significant digits, so 639. But that's degrees Celsius. That's not our boiling temperature. That's the change in temperature boiling. So what do we have to do to this? We have to add it to 100. What is the change in freezing point for a solution of 10 grams of glucose in 5.0 grams of water, which has a KF equaling 1.86 degrees Celsius per molal? So again, we need to find the molality. 10.0 grams of glucose, C12H22, I'm sorry, that's sucrose. Glucose is, and I would give you the formula for this in a testing situation, C6H12O6. So then we need to take every, we're trying to find molality. We need to find moles per kilogram. So we have 50 grams of water. And up here, we know that every 1,000 grams of water is 1 kilogram. 6 times 12.01 plus 12 times 1.01 plus 6 times 16.
It's 180.18.
This is the molar mass of glucose. That's equal to 1 mole. 10 divided by 50 times 1,000 divided by 180.18.
It's about 1.11.
So we get 1.11 for our molality. Now, glucose, carbon is a nonmetal, so this is not going to separate. So the index is 1. Molality is 1.11. And we have the K sub F is 1.86 degrees Celsius per molal. One times 1.11 times 1.86.
It's 2.0646.
2.06 degrees Celsius as the molality cancels out. But this is not our final answer, as that is the change. So we take 0 minus that, and we get negative 2.06 degrees Celsius. The Van Hoff factor for K2SO4, we have 2 Ks plus 1 SO4. So that is equal to 3. We know that K is potassium, which is a metal, so that does dissociate. A solution of NaCl in water freezes at negative 3.72. What is the molality? Well, delta T sub F equals index times molality times K sub F. We are trying to find the molality, so we need to divide both sides by the index and K sub F. Here, that will cancel, and that will cancel. The molality then for this one will equal the change in temperature freezing, which we will change to 3.72 degrees Celsius. The index for sodium chloride, sodium is a metal, so that will be 2. And the K of F is always constant for water, 1.86 degrees Celsius per molality. 3.72 divided by 2 divided by 1.86.
The answer is 1.
The answer for this then is 1. The molality of this solution is 1 molal. Last problem, 25 grams of KCl is added to 100 milliliters of water and dissolved. What is the freezing point? So again, we're playing the same game again. We have 25.00 grams of KCl. We have 100 milliliters of water. We know every 1 milliliter of water is 1 gram because of the density of water being 1. And every 1,000 grams is 1 kilogram. That will give us molality. 25. Oh, it will not give us molality because I need to also change the grams of KCl to moles of KCl. 35.45 plus 39.10.
It's 74.55.
74.55 grams of KCl is 1 mole of KCl. 25 divided by 100 times 1,000 divided by 74.55.
It's about 3.3534.
3.353 molal. Oh, it's 100 dots. So all we need is 300 significant digits there. So remember, delta T sub F equals I times K sub F times molality. We have the I since it's KCl and that's a potassium, so it's 2. We have the molality, we have it right there, we just solved it. And we have the K of F because it's a constant, 1.86 degrees Celsius per molal. Molality cancels out. 2 times 3.35 times 1.86.
It's 12.462.
12.46 is not our final answer. Actually, 12.5 is not our final answer because we need to subtract that from 0. 0 degrees Celsius minus T of F or delta T of F equals negative 12.5 degrees Celsius. That's what we've got for today. If you want the answers to, if you were, this was optional. If you want the answers to that, there they are. Yep. So there they are. If you have questions, by all means, stick around. Otherwise, make sure that you are following the schedule for today.